this particular lesson, we're going to work on basic trigonometric equations. But first, let's define what I mean by trigonometric equation. Any equation that contains a trigonometric function is called a trigonometric equation. So one example is sine of x is equal to 1/2. This particular equation contains the trig function sine of x, so it's going to be called a trig equation. We've also seen several other types of trig equations. One of the more important ones that we've used quite a bit is sine squared plus cosine squared is equal to 1. So this is an equation, and it contains both trig functions, sine and cosine, so it's going to be called a trig equation. It's going to be beneficial for us to distinguish between two different cases. The first case is the trigonometric equations that are called identities. For example, sine squared of x plus cosine squared of x is equal to 1. This is called a trigonometric identity because it works for all values of x. In the next few lessons, we want to deal with trigonometric equations that are not identities. In these cases, our goal is to try to determine the angle measure x. So for example, sine of x equals to 1/2 is not true all of the time, so we're interested in figuring out the values of x that do satisfy this equation. So from now until the end of this chapter, we're going to focus on how to solve trigonometric equations that are not identities. For the remainder of this lesson, we're going to look at our basic trigonometric equations. This means we're going to focus our attention on the following three situations: when sine of x is equal to some number, when cosine of x is equal to some number, and when tan of x is equal to some number. So let's develop strategies to solve these particular types of trigonometric equations. Let's take a look at the procedure to solve our basic trig equations. Our first step is to use the cast rule to determine which quadrants we have to consider when solving the question. Often what's going to happen is our trig function is going to be positive or negative in two different quadrants. So using the cast rule is going to help us narrow down our view and determine which quadrants we actually have to consider. Next, what I tend to do is draw a right-angled triangle and use the two special triangles, the 1, 1, √2 triangle and the 1, 2, √3 triangle. Of course, it's also acceptable here to draw a triangle and use the unit circle and reference angles to help you solve. Our last step is apply a periodic solution if it's necessary to do so. So the best way to explain this procedure is through a couple examples, so let's dive in. In this example, we're going to solve the equation cosine of theta is equal to 1/2. First, we're going to do it on the interval from 0 to 2 pi, and then what we're going to do is give a full solution that includes every single one of the possible answers for theta. So, according to our procedure, the first thing we have to do is use the cast rule to determine which two quadrants we need to consider on the interval from 0 to 2 pi. What we know is that cosine of theta is a positive value. So, that means our quadrants that we're going to consider are here and here. We're not going to have any solutions in this quadrant or this quadrant because in these two quadrants, cosine is a negative value. So first, let's try to solve cosine of theta equals 1/2 in the first quadrant only. So here I've drawn my reference angle, and I know that I have the relationship cosine is adjacent over hypotenuse. So this means for the right-angled triangle that I have here, I know that the adjacent side is 1, and the hypotenuse is 2. So what we have are the first two parts of a 1, 2, square root 3 triangle. If you don't happen to see that right away, you can always use Pythagoras' theorem to find the missing side length here. Now that we know we have a 1, 2, √3 triangle, we can try to figure out the value of theta. So in this particular case, theta must be equal to 60 degrees, or pi by 3 radians. Now that we have the values required in the first quadrant, we can use this value for theta as our reference angle in the fourth quadrant. So notice here that I've just reflected my right-angled triangle downwards, and I know that this theta value down here must be equal to pi by 3. So we need to figure out this angle traced out in blue. Well, a full rotation would be 6 pi by 3s, so this angle that we require down here must be 6 pi by 3 minus 1 pi by 3. And that's equal to 5 pi by 3. So on the interval from 0 to 2 pi, we have two solutions. The first one is pi by 3, and the second one is 5 pi by 3. Now that we solved the equation cosine of theta equals to 1/2 on the interval from 0 to 2 pi, we might ask ourselves the question, what are all solutions to the equation cosine of theta is equal to 1/2? So what we're going to utilize here is the fact that cosine of theta is going to repeat every 2 pi radians. This means that our full solution for our original equation is theta is allowed to be the value of pi by 3. And this particular solution is going to repeat every 2 pi radians. So to write that it's going to repeat, we're going to attach 2n pi to pi by 3. And here, n is allowed to be any integer number. So we might write n can be any element inside of z, the integers. But we also found another solution on 0 to 2 pi, and that was theta equals to 5 pi by 3, and this particular solution is going to repeat every 2 pi radians as well. So by stating 5 pi by 3 plus 2n pi, that's going to get all of the repetition for that particular solution. So in blue is the full solution to this problem. Pi by 3 plus 2n pi and 5 pi by 3 plus 2n pi. Next, let's solve the equation tan of theta is equal to negative root 3 over 3. Again, we're going to begin by considering the cast rule. So what we want is we want to figure out the two quadrants where tan is going to be a negative value. Well, we know tan is positive down here and tan is positive over here. So the two quadrants for us to consider are going to be quadrant 2 and quadrant 4. So let's go ahead and draw in two triangles. And we're going to put the value of theta in here. Next, we know that tan of theta is the ratio of opposite over adjacent. We could write root 3 over 3 as 1 over square root of 3. And this is going to lead us, hopefully, to one of our special triangles. Looking at this triangle down here, we know that the opposite is going to be negative 1, and that the adjacent is going to be square root of 3. For this particular triangle, we know that the opposite is going to be 1, and that the adjacent is going to be negative root 3. Now how do I know what's going to be positive and what's going to be negative? Well, I'm thinking about movement along the x and the y axes. So for this particular triangle, I've moved plus root 3 and then downwards by 1. For this particular triangle, I've moved negative root 3 in the x and then up 1 in the y direction. And of course, this is our 1 to root 3 triangle, so our two hypotenuses here are going to be 2. So the next thing we have to do is try to figure out what our reference angle theta is going to be. So since we're in a 1 to root 3 triangle, and our angle theta is across from the leg of the triangle that has length 1, it must be that theta is 30 degrees, or pi by 6 radians. Now that we have our reference angle, let's actually try to figure out the angles that we need on 0 to 2 pi. Beginning at the value of 0 radians, we can move over this way. So our first angle here must be 6 pi by 6 minus pi by 6. That's going to be 5 pi by 6. And then our second angle begins at 0 and goes all the way around over here. This is going to be 12 pi by 6 minus pi by 6, or 11 pi by 6. So on the interval from 0 to 2 pi, we have that theta is either going to be 5 pi by 6, or theta is going to be 11 pi by 6. Alright, now let's finish up this question by trying to figure out all of our solutions to the original equation. Remember that tan of theta is a little bit different from sine and cosine. Sine and cosine repeat every 2 pi radians. However, tan repeats every pi radians. This would imply then that all of our solutions might be given by the following: 5 pi over 6 plus n times pi. Here n, again, is any integer, or 11 pi by 6 plus n pi. But we run into a little bit of a problem here. What happens when n is equal to 1? Well, if n is equal to 1, this value of theta becomes 5 pi by 6 plus 6 pi by 6, which is equal to 11 pi by 6. And that's exactly this first solution we get here when n is equal to 0. So what we're going to do is we're going to eliminate this particular solution because it arises when the value of n is equal to 1. Now that we've gotten rid of that duplicate solution, we can say that our final solution is going to be 5 pi by 6 plus n pi, where n is any integer value. Alright, my little epsilons, stay positive.